Eckhart Tolle once said, "We are not in the universe, we are the universe, an intrinsic part of it. Ultimately, we aren't people, but rather focal points where the universe has become conscious of itself. What an amazing miracle." End quote. Later, Carl Sagan stated, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies, all came from the center of collapsing stars. We are stardust." Now, when I saw these quotes on Pinterest, whenever Mr. was talking about the star cycle, I had this, philosophical, I guess you could say, realization or something like that, that we're, way more like everything else in the universe than we originally think. It felt like I had taken the X and Y axis that everyone, thinks on and, put a Z axis through that, and it was just sort of mind-blowing, and it sounds totally crazy, and I'm pretty sure all of you right now are going, "Holy crap, Allie is an idiot, and she probably was on drugs whenever she thought of that." But when it comes down to the basis of living things, evolution, social interaction, and biological integrity, every species, whether Platyhelminthes or Chordata, is remarkably similar. Everything behaves the same, which is pretty widely recognized and taught, but what isn't, to my knowledge, is how stars behave really similarly whenever you observe their evolution and their behavior. They're the only non-living thing that so closely imitates the determination of living organisms to survive. When I thought about this, I immediately knew that my project was going to center around this idea. And so I started researching, and the more I researched, the more past me talks, the more current editing video me hates past me. So to get down to the freaking point, we're similar to stars, and stars are similar to us. So this video is going to have a lot of comparisons of humans and stars. The more that everything narrowed down, with this metaphor, I suppose you could call it, and the stronger it got.
The explanation begins here at Sand Creek High School, or as I like to call it, Nebula SC97.
There are multiple types of nebulae: dark, emission, reflection, and planetary. All of them are pretty similar besides temperature, color, radiation. Okay, they're pretty different. Emission nebulae are characterized by the fact that they, as the name suggests, emit their own light through the ionization of the neutral hydrogen molecules by the rare O and B type of stars. This type of nebula is around 10,000 Kelvin, and like its counterpart, the reflection nebula, is quite star fertile. A reflection nebula has a similar composition to that of an emission nebula, but it's not ionized. Instead, the light you see from it is the gases in it reflecting the light from stars. Then there are the dark nebulae, which are so dense that they obscure all light that comes from behind it. A planetary nebula is at the time completely irrelevant because it's part of the star cycle and not an original nebula. But don't worry, because all nebulas are created equal and composed of dust, plasma, helium, and hydrogen. Nebula SC97 is a reflection nebula due to the fact that administration isn't too bright and all the glory comes from the students inside. Stars in this nebula and other nebulas start to form when a disturbance in the ISM causes molecules in the nebula to bind together, and over time, after the fighting of potential and kinetic energy trying to expand and condense matter, a core is formed, and hydrostatic equilibrium is reached, resulting in a final massive shock wave that disperses the protoplanetary disk surrounding it. But we're not done yet. Infalling matter continues still, increasing the size of the protostar by a factor of 100. The growth comes to a halt once the thermonuclear fusion begins and stellar winds start, which is also when it becomes a main sequence star. Comparing a protostar to a person is easy, but hard to explain. So, I'm going to try my hardest to explain that. Freshman. Protostars?
I don't know why he wants to fight me, since he knows I'm better than him.
Yeah, bros, I can be bros like that.
My mom just doesn't understand. I'm an adult now. Where are the bathrooms again?
When a protostar matures, it has two paths to choose from. If it's not able to size up to the tasks at hand, it'll become a brown dwarf. A star that isn't a star, isn't going anywhere in life, and is well aware of that. Sadly, this is what happens to most protostars. However, if it does succeed, it moves on to another kind of status. Main sequence. This is whenever a star is actually considered a star. Allie, why is that in your video? Because it's a mnemonic to help you remember the spectral classes, and now that you've seen my cat reject me, you'll never forget it. The spectral classes are O, B, F, G, K, and M. O being the hottest, and M being the coolest. Now, of course, I'm talking the Hertzsprung-Russell diagram here, which is how we organize stars. And the spectral class is the color and therefore temperature of the star. These letters are then further divided into sections 0 through 9, with 0 being the hottest and 9 being the coolest. But wait, there's more! If you're already confused, just wait what I'm about to throw at you. The spectral class has a buddy called the luminosity class, and it's repped by no other than confusing Roman numerals. Okay, it's not that confusing. 0 is for hypergiants, 1 is supergiants, 2 is bright giants, 3 regular giants, 4 is subgiants, 5 is main sequence, SD stands for subdwarf, and D obviously stands for dwarfs. Let's review, shall we? Meet star B0Z. She's hotter than a midsummer day, and as all O and B stars are, she's rare enough to be in an animal collection.
Did you know that 90% of your body mass is stardust because all of the elements except from hydrogen and helium are found in stars?
What? Stardust? That's
Did
crazy.
I mention how bright she was? Now we observe M7V. He's, the opposite of hot.
Anyone really been as far as even decide how
And,
to
well,
do it?
dumb. The opposite of bright. Now that we have classification down to a high school astronomy 2 class science, we can move on to the actual star cycle. On to main sequence. But what makes a main sequence anyways? Like, out of all the stars, why are those stars main sequence stars? And why are they what they are? To explain this, I'm bringing back this beautiful diagram, and when you look at it, you're able to recognize the locations of various types of stars. But look closer at the main sequence. The stars are arranged in a defined diagonal formation. Other stars aren't. Still don't get it? The other stars are outliers, just like in math. All these stars are average, and conform to a pronounced rule that luminosity decreases with temperature. Whereas other stars don't. The most common type of main sequence star is the red dwarf. These stars are immortal, the cockroaches of the universe. Not even a nuke could make them leave.
15 years?
Why did you say it like that?
They go on their own terms, and their mass ranges from 7.5% to 50% the size of our very own Sol. Legend has it they'll one day stop being cool and will heat up, suddenly getting hot and blue. But I'm not sure how that'll go down. No one is, after all. It is just a theory. Stars greater than or equal to 200 times the mass of Sol fuse elements all the way up to iron, and their main sequence stage is usually a blue supergiant, and they have an ironically small life. Yellow dwarfs and other sun-like stars advance to the red giant phase because of the pressure caused by fusing helium into carbon. Ever tried the Kylie Jenner challenge? Same thing, sort of. During the challenge, your blood is sucked into your lips from the vacuum pressure created in the shot glass. In expanding stars, after a certain point, equilibrium starts to break the further the layers get from the gravitational pull of the core. The vacuum of space continues to pull, which is what creates planetary nebulae and causes your lips to bleed. When it comes to the large, massive blue supergiants expanding, they don't. They simply begin to cool to red supergiants, unless they're super duper blue giants, in which case they burn through their fuel so fast they just explode into a supernova and become a black hole or a neutron star. A medium massive star's life is much more complicated. Once a plain red giant expands into a planetary nebula, the surrounding cloud eventually disperses, and a glowing, dense white dwarf. Wait, no, not that kind of white dwarf. Yeah, that kind. That white dwarf remains as one does at the end of all lower mass star lives. This white dwarf eventually fades into a black, burnt-out dwarf, and that's the end. Unless the star isn't alone. This is the case with many stars, and it's called a binary star system, in which case life is way more complicated. These stars are inseparable and orbit around each other. Eventually, the more massive one begins expanding, as usual, into a red giant, engulfing and smothering the less massive star. The smaller star and the star core then circulate within the shared gases, and eventually the envelope is ejected, and the core becomes a white dwarf. The companion star grows, the white dwarf reaches critical mass, and it results in a supernova, ejecting the companion into space. That relationship ends in a big, big bang. This supernova is known as a Type 1a supernova, whereas the other Type 2 supernovae result from an incredibly large mass becoming unstable. If all those comparisons don't convince you that we're made of stardust, I don't know what will.